to the rest of the state permitting process. Depending on the size of the project, the DPU through the Energy Facility Siting Board could be involved. Those thresholds are relatively high, but typically a 100 megawatt project would have to go through the siting board, and there are also limits for the transmission side of the project based on length and voltage. So for a smaller project in state waters, you typically would not be involved with the siting board, but larger projects, as in the case of Cape Wind, was obviously involved with the siting board, although not for the wind turbines, strictly for the transmission cable that brought the power ashore. Another agency that would be involved, obviously, is the Office of Coastal Zone Management, and the determination for consistency with the coastal policies, but also under the new Massachusetts Ocean Plan, which is a rather comprehensive document that delineates areas within state waters and makes some recommendations also for offshore federal waters where wind projects would be allowed. Also has areas where they would not be allowed, and then kind of another area where if they can meet certain performance standards, then they may be allowed in those areas as well. Continuing on with the Department of Environmental Protection, permit that has to be obtained there. They look at a number of issues there. They have to issue essentially something that you might think of as being equivalent to the lease that BOMA issues. It's the Chapter 91 waterways license that would allow the project to be built within the state waters. They'll also look at biological resources. They offer the water quality certification, as well as in some cases look at air quality concerns associated with the project. Some of the other agencies, obviously Fish and Wildlife, and through the Natural Heritage Program for the endangered threatened species and the analysis that goes along with those and investigations there. The Historic Preservation Office on the landward portion of a cable, where the cable would come ashore, for instance, or any tie-in to the existing cable, as well as some potential visual situations or potential impacts from the offshore projects. And then we also in Massachusetts have a Board of Underwater Archaeology that would be interested in the potential effects on any resources offshore beneath the water. Looking at local approvals, these are typically addressing very specific interests, and depending where you are located within Massachusetts, you may be involved with a regional commission. I've listed two of them here. Cape Cod has a Cape Cod Commission, and Martha's Vineyard has a commission that could potentially be looking at these projects through their development of regional impact process. Most towns in Massachusetts would be involved mainly on the cable installation side for the project through their conservation commissions, looking at getting the approvals necessary through an order of commissions under the Wetlands Protection Act. You could be involved with zoning or planning, and then you could also get into some local permits as kind of ordinary and mundane, if you will, as a simple street opening permit to install the cables to tie into the existing system and bring the power ashore and get it into the local community. One thing that on the local side, obviously the local community as well as local officials have a significant role as participants in not only the state but the federal process. And so for developers and people looking at bringing into a project into an area, it's always good to recognize that and make sure you have good interactions with the local community and local boards and commissions. Just briefly now, I just want to go through a couple more slides. Excuse me, just kind of looking a little bit at the analysis that you would need to look at in very general terms to kind of support some of these permitting activities that we've just listed here. And without going through these in any detail, obviously there's engineering and structural alternatives that have to be looked at and addressed in any of these permits. Typically construction, how you're going to do it, what's the operation going to be like, what about decommissioning, Those all have to be addressed in these applications. System impact study has to be done to see what is the injection of the power from your project going to do on the local system, what kind of upgrades may be needed, and if there are significant upgrades, what level of approvals might those need in addition to what your project needs. And then obviously, through most processes, not just the federal but the state processes, there has to be a demonstration of at least some sort of an alternatives analysis, looking at siting alternatives, alternatives for cables, and different project configurations. And so here just briefly listed some of the field programs, as we call them, that would have to be undertaken to develop a lot of the data that would feed into these permit applications. And these fall into a number of different categories, but just briefly here we have the geophysical and geotechnical program that would be run offshore in order to be able to determine water depth and bottom conditions for the, to help with not only the permitting but also the design of the project. What kind of foundation are you going to need given the bottom conditions that you might have in the particular location of your project? Obviously offshore resources have to be evaluated as well as upland because of the, again, the cable piece of the project. I think as we all recognize, avian concerns with wind projects are kind of in the forefront, so we have to look at avian investigations and a number of studies there, either phase 1 assignments or possibly some longer term monitoring might be appropriate. Sound level analysis, visual impacts, and historical and archaeological investigations, both onshore and offshore, to provide the information that is needed for addressing these applications. So finally, the last slide here just kind of gives you a list of what I've called typical approvals for a project in state waters. And as you can see, it kind of cuts across the board. Federal, state, and local approvals would be involved. Corps of Engineers, the FAA for clearances on the height of the structures, Coast Guard, because once you've not only addressed the navigation concerns, you also have to potentially file with the Coast Guard for under the aids to navigation for the new structures that are put into the water. EPA potentially through discharge permits. And as we've already mentioned, the DEP, Chapter 91 Waterways License, 401 Water Quality Certification, Coastal Zone Management, local conservation commissions for the order of conditions under the Wetlands Protection Act, and then potentially, as we mentioned earlier, street opening permits through the local DPW or the local authority. So thank you for your attention, and appreciate the opportunity to be here.
Questions? Yes.
I have two questions.
Do you want to use the mic there, Jim?
Sure.
Want to use the Jim there, Mike?
Hi, I've got two questions. The first is to Bob, and the second is to Steve and or Jim. To Bob, the question is, how does
this wireless thing work?
how does this thing work without screen?
Hello, check.
Feedback from the
Feedback.
Oh, okay.
If you just move.
Put your hand up.
Just,
Yeah.
Let's try this. Okay. I'm wondering to what extent your agency works with the IEC in the development of standards, offshore wind turbine design standards, and if you're going to participate in the development of the second edition. So that's the first question. That's for you.
Okay. We are working with to move ahead on that. I'm not quite sure what our exact status with IEC is, but we have, as I mentioned, engaged the National Academy to give us advice on what we should do about standards. We've had a couple of workshops, I believe, along with DOE, and you know, we're trying to learn, take the best from what Europe has done, but also apply it, as you would imagine, to our specific conditions off the U.S. coast. So I can get you some specifics on the IEC a little bit later, but I don't know off the top of my head.
Great. Okay.
Yep.
And the second question has to do for you other two on the permitting. It seems to me that Hull is kind of unique in its location in state waters and its history of a lot having happened already here in terms of studies. So how would you compare or contrast the ease of getting a permit for Hull for an offshore project versus somebody starting a new project off the outer continental shelf?
Well, generally speaking, anything in state waters doesn't need BOEMA approval, so that's one thing that's out of the way. Seems like Hull has developed a lot of expertise from its existing wind farms, and that will be a major asset in terms of any sort of application for wind farms, either in state waters or federal waters. Hull seems to be very far advanced in terms of that. The other projects, wind farm projects, they're all private entities, and I'm not aware of any towns, so this is totally unique. And I think the experience that you have would serve you very well in the permit process.
Yeah, and I would just add to that, Jim, in that I think, you know, Hull would have an advantage in going through the process because of the data that has already been developed. So they have a base to work from, in other words, at least in terms of maybe shortening the time period a little bit, because they've collected a lot of data, have a lot of good information already from which to start from, don't have to go back and recreate all of that, so to speak, in order to go through the process. So I think as comparing Hull against some new location, I think Hull would definitely have an advantage.
Other questions?
Same for Mr. Steve.
I don't, sure. Go ahead and state your name and
Hi, my name is Sylvan. I'm a resident here, also working in wind turbines. If you go back in one slide, please. Let's go back one. Here we go. Typical approvals. Talking of Hull, where could you give us an overview where, if you have an idea, where we would stand in terms of having a certification to have something which would be which would allow outgoing, I mean, in real world. Now, you talk about, okay, it's going to be easier, blah, 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 but in terms of timing, how long would it take to have those things happening? If let's say that Hull would go further with a project of offshore wind turbines.
If you,
I'm going to stand up.
Yeah, or you can use, I was going to bring you this. You got it?
I mean, the easy way to dodge that is to say it's a difficult question. But
it depends.
or as Ruth would, as
depends.
my lawyer would say, it depends. Well, and I think it really is hard to tell. But I think my point to Jim was that you know, because of some of the original work, as I think most people in the room know, there was some original work done for an offshore project in the town of Hull.
Actually, Steve, we've got a little bit of time if you want to just mention some of that work.
Okay.
That's fine.
Yeah, I mean, there was a project that that started through the permitting process. Actually, you know, got quite a ways through it, I guess I would say, at least at the state level, for a 4 to 5 megawatt. I'm sorry, 4 to 5 turbine, 12 to 15 megawatt project off the right out there, and it got. I guess what I would call maybe halfway through the MEPA process. The environmental notification form was filed. There was a good interaction with the agency. A task force, a TAG as it was called, was formed to help define the studies that needed to be undertaken for the project. TAG was Technical Advisory Group with MEPA as the lead. On that. The Corps of Engineers participated in that as well, and a number of other state permitting agencies. And that was done under the certificate that was issued on the environmental notification form. A number of studies were completed before the project basically, you know, went on hold, so to speak, for funding reasons. So a number of these things were completed. For instance, the FAA determination of no hazard for the height of the turbines was received, so that, you know, that box was checked, if you will. We had, let's see, what else have we gotten through? We hadn't got to the point of getting to most of these other approvals yet, but my point to Jim was that a lot of the data needed not only for the design and construction, if you will, of the turbines vis-a-vis the foundation type. A lot of data was collected for that, but that data was going to be available to provide input into, you know, the core permit and into the final MEPA EIR, which ultimately would have led to the certificate. So, you know, exactly where we are and how much more time would you need is kind of hard to say at this point, because things have changed a little bit. There wasn't the one new thing that has come along since that all started was the ocean management plan. So, you know, there's some new things that are in there now too. But, you know, suffice it to say, if we were starting from scratch today and hadn't done any of that previous work, you know, we're probably, you know, a year or more up on, you know, what a comparable project might be.
Okay, maybe a little follow-up, Steve, with Bob and Jim. How important, if I were to move forward with a facility, whether it's a commercially producing facility, a test tower, a platform, the process, it's so new. We hear a lot about Cape Wind, and deep water wind is going through now, and some of these other, but how effective would it be an asset to the feds to have a project be permitted and built off the coast here?
I think it'd be very valuable. I mean, I also think that the one thing that you have to realize that
Hold on. The question was, how valuable would it be to the federal agencies to have something in Hull, either and Andy, I don't want to put words, but a platform, a test tower, another not a demonstration project, actually a real project, maybe, you know, just further out, but within the State Water Hull Municipal District boundaries.
Right, and I think it would be very valuable, you know, in terms of public acceptance, that there is a fair process by which concerns can be aired and decisions can be made and something can actually go forward. I think, you know, Hull has already sort of taken really good steps down that road, and if you're successful in doing this offshore project, I think it's going to help very much in terms of putting it on, you know, in the national public's mind. The other thing I wanted to mention is there's a similar project in scope that it's a pilot project that they're planning off Block Island to put a 3 or 4 turbine. I think it's deep water. And so I'm sure many of you are aware of that, but there are some parallels here in trying to get that in the water. So.
The Corps has a very abbreviated permit process. In fact, a nationwide permit for things like meteorological towers. Our nationwide permits are up for reauthorization, and they were recently published in the Federal Register. The comment period closed, I think, about a month ago. As part of the process, this specific nationwide permit does specifically mention meteorological towers. So it's a very, very abbreviated process as far as we're concerned. We're also contemplating a new nationwide permit for pilot projects for renewables. You can look at the Federal Register notice to see what's proposed. I don't want to go too much into it because we're still under deliberations with it, and we don't know what the final outcome is going to be. We're sifting through the comments now. We got tens of thousands of comments, but if there is a nationwide permit for a pilot project, that too would be a very, very abbreviated process. So that would help it move along a lot more quickly.
Time for one more? No? One more.
I was curious about the memo of understanding that you mentioned regarding the fishing Fish and Wildlife Service about migratory birds. Does that include, have you already mapped out, say, the coast of Massachusetts and what areas are sensitive and not, and others?
So the question is about the MOU between BOMER and Fish and Wildlife and whether the coast of Massachusetts has been mapped out for purposes of the Migratory Bird Treaty Act.
Just going back to why we did that, the Act itself requires Fish and Wildlife to develop MOUs with all the federal agencies that are involved in coastal and ocean issues. And we are very proud to be, I think, the second agency to finish the MOU with them. And they're working on, I think others have joined since then, but to answer your question, we're working very closely with the Northeast Fish and Wildlife folks, migratory bird folks, as well as the endangered species group in Fish and Wildlife. We're learning more about where the areas of concern are. You know, by definition, migratory species are not in typical, well, they can be in typical locations at certain times of the year. So, but you know, what the main message was is that we needed a lot more data. And Fish and Wildlife for years has been saying this, but hasn't had the resources. So renewable energy is actually providing some of the interest in renewable energy is providing some resources to study and improve the baseline information. And if you go on our website, you can find at least, I think, 3 or 4 major studies that we've already finished or we've got underway to better learn where the areas are, you know, the hot spots are for migratory birds.
Great. Well, please, I think, join me in thanking the panel. The panelists will be here to continue to answer questions. I can't thank you enough. This has been terrific. Thank you very much.
You bet. Thanks. Great guys. Thank you so much. All right. It's a cool hat. Yeah, you know, one of a kind. That's right. Very cool. Jim. All right. Thank you. All right. See you. Please join me in thanking the panelists again. So we're a little ahead of schedule, which is fine. We're due to go to lunch at noon, so we can break a little early. Lunch is from 12 to 12:45, and we'll have 2 featured speakers. And lunch at noon will be served downstairs, immediately below this floor. Thank you very much, and we'll see you back here around at 1. We have the 12:45 featured speaker. Thank you. I'd like to remind the speakers to maybe take a step towards the mic and enunciate. Let's get some levels back to the back of the room. How did everyone enjoy lunch? Paid for with Obama bucks. We'd like to continue this afternoon's program. We're a little behind, but that's okay. I think there's a lot of knowledge transfer here and some pretty good questions and the ability to interact with the speakers. Our next speaker is one of the directors of the Renewable Energy Labs out at UMass Amherst, and Jim Manuel and his team have been integral in the 2 turbines that you see onshore, as well as some of the studies and visualizations of the machines that will be installed offshore. And I'd like to take this opportunity to turn over the floor to our other featured speaker, Dr. Jim Manuel.
Well, thank you very much, Andy. I like that word you used, will. You know, that's will be installed. So we're hoping that is really going to happen. And I've been at this business for a long time. I started, I had lots of hair and it was all red at the beginning, I think, when I first came to Hull. I'm not sure that's true, but we'll say it is. Okay, so I'm going to give a little bit of history here, but hopefully a history that will continue into the future. I call it a retrospective on the design and permitting of the offshore wind project. And again, everybody has a hard time with this, so I'll see if I can. I did it. Okay. Where are we? We're in Hull, obviously, and this I just wanted to point out on a map where Wind 1 is over there at Windmill Point. We heard about the history of that before, and down there, kind of inland, on a relatively shorter tower at the old landfill is Hull Wind 2, and then off the coast here, and then off Nantasket Beach is where we're proposing the offshore wind farm. And gee, I have to mention Nils Bolgen is here. He was there even before I was, I think, in Hull, and he sent me here many years ago. He said, "These guys want to put up another turbine. I can't believe it, but they threw me out last time. So Jim, you go." So so that was the story, and so here I am today. Okay, so this is the general area off Nantasket Beach is where we're focused. So what was the project, or what is the project as we viewed it? Well, it was going to be up to 4 wind turbines, and again, there's a history of why it was 4. John McLeod, who used to run the light department, and I think people thought he just kept wanting to put up more turbines all the time, and somebody said, "Stop, you got to give us a number that you promise you won't put up any more than that number," and he set 4 at that point. So that was one of the reasons. But there was a more serious reason, because we were looking, and I'll say a little bit more on that, is turbines, there were to be GE turbines, 3.6 megawatts, and the total of 4 would add up to what looked like the right number that the power grid would accept without major modifications. So that's how it all started, but 4 was the number that we were looking for, and as the project evolved, we were just looking at something in the 3 to 5 megawatt range. You know, as time marches on, turbines do get bigger. We just saw today that GE's turbine, their next offshore is 4.1 megawatts, and their last one was 3.6, so they do get bigger. Okay, so the idea is installed in the vicinity of Hardig Ledge. Hardig Ledge is a bunch of rocks right out there that, as you heard before, that the good people of Hull back in the 1700s would build fires on the shore, and I guess put bells or lights on the necks of the cows so that, you know, that these stories, so that the ships would come close and then crash, maybe on Hardig Ledge, and then people would go out there and scavenge the wrecks. The suggestion was made, if we put these turbines around Hardig Ledge, then you couldn't possibly bump into them anymore, because you'd see the turbines. So we were looking to somewhere in the beginning around 12 to 20 megawatt generating capacity, and one of the ideas that we kind of liked was thinking that the energy production on the average would approach 100% of Hull's electricity consumption. That seemed like a nice number to aim for. 100%, I kind of like that, makes me feel good. So that was the thought. We also had to start thinking pretty early about what's real, of course. It's nice just to think grand ideas and things like that, but you have to think about reality. And so we were thinking of what the turbines are really likely to look like and what their support structures are. And so I just want to point out a couple of things here. We talked a little bit this earlier in the day, but there were fundamentally, for a place like Hull, are 2 real options for the support structure. Does this? Let's see.
Point to the computer.
Which? How do I get the red? No,
right in the center.
Oh, right in the center, okay. Okay, so most turbines installed offshore today are on these monopiles, big pipes basically that are pounded down into the ground, and that works out pretty well. The cost is generally that's one of the lowest cost options. If you're a fish swimming by, it kind of knocks you senseless for a little while, but you can get up and swim away. But at any rate, they do make noise when you're hammering them. The other type that really are the most common, second most common, are the gravity foundations. These are big chunks of concrete, reinforced concrete, essentially, that are put out there in the sea. So those are the 2 real options. These other kind of multi-member structures, sometimes called jackets, tripods, different things like that, didn't really seem to be what we would use in Hull necessarily. The water's shallow enough; you don't have to go that far. So we had these 2 options to think about. So what's the project history? Well, this really started in 2003. It was modeled on 2 Danish projects. The Middelgrunden project is right off of Copenhagen, Denmark. It has 20 turbines built by Bonus, which is now Siemens, I believe. And Samsø is an island in Denmark. It's connected to the grid, so in that sense, it's a little like Hull. I mean, Hull's connected to the grid too, of course, even though it's way out here in the water. But they had a goal in which they achieved of supplying 100% of their energy on the average with renewable energy, and they have a small offshore wind farm, a little bigger than what we're talking about here. But anyway, the ideas seem kind of similar. So, based on, as I said, four 3.6 megawatt GE turbines. Ben Bill of GE was working with us in those days. He was another. I didn't tell you about the history of the UMass Wind Energy Program. I always had to put in a plug. We've been working with wind energy for since I was a pup. Well, that's exaggeration, but at any rate, since the early '70s. At any rate, and a lot of our graduates have gone on to work in the wind industry, U.S. Department of Energy and National Renewable Energy Laboratory, and lots of the companies and whatnot. So anyhow, Ben Bell was one of the guys working for GE. We did our first filing, believe it or not, with the Army Corps of Engineers, or at least first meetings with them back in 2003. But then the project sort of slowed down for a while, but we kept it alive in our minds anyhow. Then we got some funding, a loan from the Renewable Energy Trust Fund. Again, Nils Bolgen back to work, helping us on that. And he was the contract monitor for a lot of these studies that went on. And at the same time, we were lucky to get some support from the Bureau of Reclamation to do a wind and a desalination study. Hull was very interested in getting fresh water from desalination, and so we thought, what an interesting idea, combine the two, at least in a conceptual way, the offshore wind and the desalination project, which would need a significant amount of electricity. So not a lot of studies happened, and the result of those was a certificate that was issued from the Executive Office of Energy and Environment. And the certificate basically said, do some more studies, but if you do the studies, we'll probably give you a permit. I mean, it didn't say exactly those words, but that was the implication. And then there was the last major thing, I think, was a financial study by La Compro, which kind of took a close look at what the cost of offshore wind turbines were likely to be based on some European experience, the price of or the value of the electricity and all that. And you take a close look at that, and it's no surprise, as offshore wind is expensive. And it's close. It was close according to some of the scenarios, but it's still not that cheap. And so we really have to figure out ways how to make the project fly. So it's not a slam dunk. You know, wind on land at Windmill Point for $750,000 for a 660 kilowatt turbine. You cannot beat that, just period, anywhere practically. That was wonderful. So offshore is difficult. A lot of people have been discovering it's difficult. But that doesn't mean you shouldn't do it. Like if you're an engineer like me, you know, I love difficult problems, right? And if they're not difficult, why bother? So this is a good problem like that. Okay, so we looked, where could we put these turbines? Well, they had to be in the water. That was the point. And there's a number of things to consider. Suitable for commercial turbines, 20 to 40 feet deep. We didn't want the shipping lanes. We thought if it was at least a mile from shore, then people would like it more. Now, we don't actually know if that's true, but it just seemed like a good idea at the time, a mile from shore. Obviously, the turbines on shore are a lot closer than a mile from where people live, but it seemed like a good idea. And then we wanted to keep it as close as possible to where the cable would hook in. And there were a couple of good points on land that looked like it would be suitable. So that was what we were thinking. And Nantasket Beach looked like a good place to go. People could see it from the beach, and that's good. So I wanted to, there's a number of considerations of impacts that you wanted to minimize: the marine environment, human activities. You don't want to get in the way of fishing, boating, and whatnot, ships and things like that. Wanted to maximize the wind speed, and that really means getting as far as you can from shore. So it's just a trick. Once you get to land, the wind starts to slow down typically at kind of reasonable heights above the ground. And we want to minimize the cost of energy. So generally speaking, the farther you go from land, the more the cost goes up, except that the wind speed is higher. So it's kind of a trick. And we developed some computer programs, again with the help of the Renewable Energy Trust and GE, the Department of Energy, that we were able to apply to this problem. So anyhow, so I should back up a little bit. So we settled on a couple areas off the coast to look at in more detail. So some of the studies that were undertaken over the course of this project were major studies on wind resource assessment, which you need to know. You need to know what the wind is to figure out how much energy you can make from your turbines, and also for the design of the turbines and their support structures. We did monitoring on Little Brewster Island, which people in Hull say is in Hull. I think people in Boston say it's in Boston. So I don't know where it is, but it's not too far from here. I know where it is, but but you know, who owns it? At any rate, and on the WBZ towers, which are these very, very tall towers that you might have seen in Hull. If you see anything really tall, it's the towers belong to WBZ. We had a lot of historical data from Boston Harbor. We've been taking data on Thompson Island, Boston Harbor, since I think 1998. And so that was real useful. There are buoys offshore and whatnot. So one of the things we did was we got a device called a LiDAR. It's the latest and greatest remote sensing devices. It sits on the ground. You don't need a tower, and you point a laser up in the air, and you figure out how windy it is and the direction at different heights. And this was purchased half with funds from the town of Hull and half from the Renewable Energy Trust. They're wonderful devices, a little finicky, but they're just great in terms of what they can do for you. They're not cheap. One of these is about $250,000 new today, so they're quite expensive. We had the first one of this type in the United States, and it was really nice to have. So here's this picture illustrates where Little Brewster is and where the LiDAR was situated, and we did a lot of data analysis to predict what the wind would be at the Harding Ledge site. And we've written papers on all these, and so there's more data available, more detail, and lots on, I think, on the whole wind website, right? You got a lot of these papers there. I'll say, okay, so there was wave and current data. You need that. It doesn't give you any energy, but you need to know it when you're designing your support structures. So there's various devices you can use, and so what we did is we purchased it's called acoustic Doppler profiler, or sometimes people put a C in there, current profiler, ADP, ADCP. Put it in the ocean off there, and did a lot of wave monitoring. That was a great experience for all of us, but we got a lot of good data from that, and there it is being deployed. This looks like the monitor. It looks like the Civil War, doesn't it? Nobody's shooting at it. Remember the monitor, the Merrimack? Anyhow, that looks just like it. So we threw it off the edge. So the only trouble with getting the data is you have to bring it up to get the data out and change the batteries. So that's a little inconvenient, but it did work. And here's some of our data. We had access to a webcam, and one particular day had a storm in 2007, mid-April. And so we were looking at the waves. So it's kind of like today. Very nice. People in the wind business, they love wind, they love waves, right? I come here and I say, this is the best possible weather, right? People look at me like I'm crazy. So we measured the waves and got lots of data from that. Okay, there's a whole slew of other studies that were performed, and I have to add that this wasn't just us, of course, at UMass. There were a lot of other people involved. ESS was. You heard from Steve Woods earlier today. He did his company did a lot of the work there, and there are various other contractors involved doing a lot of this work. So a lot went on. Just summarize briefly, and I'll have some pictures. Bathymetric data, that's the water level depth, looking at the soil with acoustic sub-bottom profiling is called, vibrocores, and then boring and sampling, mapping, magnetic mapping, and seafloor imaging. So here's where we looked in the most detail. There's Nantasket Beach, you see right there, and all those lines are where a boat went up and down, making a lot of noise, so that these booming sounds would go down into the bottom of the ocean, through into the floor, and then bounce back up, and it would tell you what the soil looked like. So they made these traverses up and down, got a lot of data from that. So the various and sundry studies were done with boats like this. This is just one of them. Excuse me. And this just illustrates the picture of the instrument that was used to get the water depth data. It's an echo sounder. There are, of course, charts available, but we needed, to get much higher resolution. And I came up with maps like this that illustrated the water depth. These are in feet here. So you see, we're kind of in the range of what we thought, in the 30 to 40 foot range, typically. The acoustic sub-bottom profiling, as I mentioned, is there's a sound produced by a boomer. It's towed behind a boat, sound goes into the soil. The signal tells you what's going on down there moderately well. There's some uncertainty, and it's a bit of an art to interpret it, and somebody other than me does this interpretation for sure. So here's one of the devices that was towed. Okay, was towed behind the boat. I got to move up here, and then the vibrocore was a device that goes fairly shallow into the soil down to 6 feet. That tells really information about where the cable could go. There were soil borings undertaken with the jack-up bars that was taken out there, and a drilling rig was drilled. Holes were drilled into the bottom. We got sample borings, and this was maybe one of the most interesting and unexpected parts of the whole study is that you look outside and it looks pretty flat and level, and you think it's just the sky's level and the water level's level, and you think that the soil is going to be pretty uniform. Well, it's not, and that makes the site real interesting. Some areas you could put in monopiles. Some areas you'd pretty much have to use gravity or drill for monopiles if you wanted to do that. And some areas are pretty mucky and you couldn't really do anything. So it's a real interesting site. A bit of a challenge. It's not impossible, but it's a challenge. And that was we didn't expect. Here's a typical cross section. Kind of blue indicates softer and green indicates harder. That just gives you a sense of what it looks like out there underneath the water. Permitting. A lot of steps were studies undertaken in terms of the permitting, and I said there was a certificate that was issued. This describes all these many different topics to consider, and I'll just highlight a few. I'm going to go read this. Highlight a few of the studies that were done. There was an alternative study. Curiously enough, we had to do a study that said why you couldn't do this on land. I said it's because it's an offshore project. They said that's not the right answer. So I said okay, I'll go back, and so we had to go back and say why you couldn't do it on land. There was a greenhouse gas reduction study. This was done by Steve Connors and his group at MIT. I think Steve's still here somewhere. And basically said that you'd reduce greenhouse gases significantly and even greater than you would calculate by just using the back of an envelope. So it's always nice when your detailed studies are better than the envelopes. Okay, we did a photo simulation. I used to come to the Clarion Hotel. It seemed a lot. I came here so often that when I would walk in, the person behind the desk would say, "Where are our turbines?" And I'd say, and I'd have to kind of, I don't know. Well, any day. Anyway, I took this picture from my window in the Clarion. Well, it was then the Clarion. Now it's in Nantasket Beach. They changed the name. At any rate, so we did the simulation of where the turbines would look. So when I came back next time, I could see it. Okay, we looked at, our subcontractor looked at magnetic data to see whether there's anything like the Titanic out there. It wasn't. There were some strange things. Maybe some pipes had fallen off a ship, or a ship had sunk once with pipes on it. Who knows? But it's not an issue, it turns out. We used Sidescan sonar to see if there was any wooden ships sunk. You can't see, you can't detect a wooden ship with magnetometers. But you can see the bottom. You see all kinds of things with the sonar, and that was towed behind the boat. And there was a map produced of what was there, and there were a lot of boulders, a few lobsters, obviously a lot of lobsters, but nothing to worry about, let's put it that way. So there were some archaeological studies too, and nobody could find any evidence of Native American artifacts, and we talked about the shipwrecks. There was an electrical study, actually a number of electrical studies, that first and foremost was to see was what we talked about crazy. Could you in fact put roughly 15 megawatts into the grid without major changes to the grid? And the answer is yes, you could. Some changes, but not major. So then we looked at different options for the submarine cable to shore, and again, this would all work out. And there's no obvious and insurmountable problems discovered. There was a support structure foundation study undertaken by a company in Denmark that has done, I think, the majority, if not all, of the gravity foundations in the offshore turbines in the world. They looked, obviously, that's especially gravity structures suitable for hard soils. And we looked very closely at the idea that it could be fabricated locally in the Quincy shipyards, visited the Quincy shipyards, and determined that could indeed have worked. And it still could work. And there's various options you can imagine. In this case, we show a floating vessel that's lift the gravity structure off a barge. But in fact, they could be designed in such a way they could be floated out there and sunk in the spot. Be a very interesting experiment, especially for a small project like this. Because what I really haven't talked about and really don't have time to is the thing that's the big elephant in the room of small projects is vessels and the whole infrastructure to enable you to install and maintain these things. So it's something to really consider for the future. So this would have been an innovative idea. Fisheries, there was some fisheries study. Lobster is obviously a big concern for Hull. So there was a lobster study. There are obviously lobsters out there, and whatever one would do would have to be done with taking that into account. The reality is, once the turbines are in place, the lobsters would probably be happy enough. You don't want to disturb them, of course, but you have to consider them. But there would be more studies required of a variety of sorts of fisheries to get the permit, and avian studies still remain to be done. Economics is my second last slide. So the capital costs they're still very uncertain. Now, when we started, based on some our European experience, actually and the Middle Ground experience, we were believing that the project would cost less than it appears that it will cost. So most recent estimates are in the round of $60 million for this project. It's not necessarily out of the question. If you look at other things, that's for solar and whatnot, it's in that league or less than solar. Capacity factors would almost certainly would be higher than the onshore turbines, no doubt about that. The wind is definitely higher. We looked at the wholesale cost of electricity, which ranged from when we started this project till now. I can't tell you what it is now, but it went down at low as like 4 cents a kilowatt hour, then up to roughly 12 cents, and then down to 7 at some point. So that has a huge impact on the economics. So at the moment, it does seem that the cost, it is the case that the cost from electricity from the offshore wind turbines would exceed the direct value that you could sell into the grid for sure. Obviously, you need renewable energy credits at least, and probably more to make it fly. Again, if you look at what's what the rates are being paid in Europe right now, it's more than we would get from just the credits plus the direct benefits. So, but in the summary, we've done a lot. There's lots of studies have been done. There are no fatal flaws that we can determine at all to a project out there. The site still appears attractive for an offshore wind energy project, but probably some mixture of a project that's not just energy production alone, but research, education, demonstration, and whatnot could all combine together. If we put the right package together, it actually could have, I think, a real future. More studies, obviously, to get a permit, but I think we're on our way. There's some detailed cost estimates that are yet to be done, and I think those are important because a lot of these numbers we have are just a little bit too much based on European experience. And the ability to build something in Quincy, for example, the fact that Hull is so close to shore is an advantage. Cable laying and whatnot, I don't think those have been sufficiently taken into account. But in conclusion, we still need a plan that kind of takes into account the reality and the opportunities, and can really allow us to go forward. So, thank you very much. Did I answer the question?
Jim's going to be back in this afternoon for the wrapping it up panel. So, unless there's some pressing question, can we hold questions till then? Is that all right? We're going to move right along to the construction panel. Thanks again, Jim. Great. Can we get Rudy? Rudy and we get Jess. Great.
I am with a company called Bluefin Robotics. We're local. As of this past November, we're more local than we used to be. We were founded. We basically spun off from MIT in the late '90s. We really got under our feet in about 2000. In 2005, we were acquired by the Battelle Memorial Institute, which is a large nonprofit science organization based in Ohio. And this past November, we relocated to Quincy, so we are almost in your backyard. And what we do is we provide autonomous underwater vehicles. And what they do, and the relevance to what we have here in this community, which is what I'm very interested in, I'm just touching, starting to get our toe in the water here, is that survey work that Professor Manuel just mentioned. So that's our little itsy-bitsy piece. What we make are these little, in the kind of the middle right here, you see that torpedo-shaped guy. That's an autonomous underwater vehicle, AUVs, and they carry survey equipment, sidescan sonars, sub-bottom profilers, multi-beam echo sounders, as Professor Manuel mentioned. They do it a little differently than has been traditionally done, in that the current preferred or common method is to do a towed system where, as Dr. Manuel mentioned, you tow it behind a boat, you do these lawnmower tracks back and forth, back and forth. The problem there is that there's a lot of motion of the towed system. What an autonomous underwater vehicle does, it allows you to get quite a bit of precision, because it carries basically an autopilot. So it's got an inertial navigation or inertial measurement unit, which allows you to get geographical data accuracy to always less than 10 meters, sometimes less than 1 meter. And that in turn allows you to get very, very precise data about the seafloor that you're surveying. Usually we do it with acoustics, sometimes we do it with visual equipment. With some of the acoustic imaging equipment, excuse me, we can get resolutions of less than an inch, actually. So the top view here is with a towed body system. You see it's kind of fuzzy. This is from one of our customers' Fugo seafloor surveys. This is a survey off of Hawaii. And then down at the bottom, with our data, basically did the same thing, one with a towed system, one with an AUV. It's much more precise. The specifics, I'm not going to get into any great detail. We make a variety of platforms that's driven by the actual mission, the sensor suite, the depth. Our vehicles range in size from about 2 meters long, 150 pounds, to roughly 4 meters long, about 1,600 pounds is our biggest. We get down to 6,000 meters depth. We can also go as shallow as 3. And so there's a variety of vehicles there in the bottom. The data that we get, this is what we deliver. This is what we provide to the community. This whole process of offshore wind is enormous, and we just have, this is a little piece that I'm trying to learn more about, but I don't really know about. But this is what we will do. We will provide very detailed images to support the surveys required by the regulations, the sighting, things like that. So Sidescan sonar in the upper left. This is actually pretty poor Sidescan sonar. I'll show you a better picture in a minute. Sub-bottom profiling. What that does, as was mentioned, provides very detailed information about the composition of the seafloor. Multi-beam echo sounding. This is bathymetry, very detailed bathymetric data. This is an example of some bathymetry. This is Harding Ledge. This was surveyed last week in a day with 3 of our little vehicles, a square nautical mile. A lot of variability there. It's not flat. What we also did, which unfortunately I can't show you because the US Navy owns the data, is side-scan sonar, very detailed images up to 1-inch resolution. So over a square mile, we know up to an inch what's there. This is pretty typical side-scan sonar data. This is in, I think this is off of Broad Sound. Yeah, this is in Broad Sound, which is off of Winthrop, a little bit northeast of Deer Island, where those big egg-shaped guys are near Logan. So that's a known shipwreck. It's on the charts. And then in the same survey, we found some lobster pots. We'll see the lobsters in the traps. And that's the kind of detail that we get. We do carry optics. We sold a survey vehicle to a treasure hunter, actually. And the image on the left, that's 1,000 meters depth, 2 craft that I have no idea what happened to them, actually. This is in international waters. It's in 1,000 meters depth. It's obviously not going to be on any chart. But on the right there is an actual still image from the same survey. Unfortunately, it wasn't the boat they were looking for. So they're still looking for their doubloons, I think. And that's it. I just wanted to, that's who we are. We're local. We just, in November, moved to the Fore River Shipyard in Quincy, right by the Fore River Bridge. We'd love to have more of a presence in the community. We're small. We're only about 80 people. We hope to grow. Looking at the increase in deep water work around the world, I'm certain we will, especially in the oil patch. But of course, there's many other markets for what we do, particularly in the U.S. Navy, international navies, academics, things like that. That's all I have. It's very brief. Thank you.
Great, thanks, Josh. And next is Rudy Hall from, he's the founder of Keystone Engineering, 1988. Folks should really take a good look at Rudy's bio. He's got a lot of experience offshore installations in the energy field, wind specifically, with pilings, jacketed structures, and he's going to talk about various construction methods and types of foundations. Yes, I'm going to put you.
How does this thing work?
Which one do you want?
The one that says Hull on it.
Okay.
Hull Workshop.
This guy?
No.
Oh.
Yes. Yeah, I'm kind of happy to be here today. It's very interesting, all the conversations, all the great work that Jim's group's doing, finding information to make it easier for engineers to design foundations to support these wind turbines. I'd like to just go through some of the basic site conditions and what could be some of the limitations for construction. How does this thing work? There's several types of foundations that may be appropriate for the Hull offshore site, and we'll look at some of those different conditions. Jim's already mentioned the gravity structure and monopile, which are the first two. Those are probably the two most popular turbine foundations that have been used in Europe, the most popular being the monopile. The gravity structures have been used basically in close inshore. Another structure that's becoming more prevalent is jacket structures. Some of the first jacket structures in larger numbers, I think 30 were installed in Ormond, which is in the Irish Sea last year. There are other structures, another 45 that are being under construction in a Belgium yard. So you'll see more and more jackets. These two concepts are prototype type concepts, the suction pile concept and out-twisted jacket. These are concepts that were developed and looked at in UK round 3 for deeper water. But they may have some application here in Hull because your fabrication facilities are somewhat limited locally, and you also have limited marine assets to install some of these heavier structures here. So there may be some advantage looking at that as well. No one foundation is going to be appropriate for all wind farm sites. And so there's many factors. Basically, there's site conditions, and we'll go over what they may be. The turbine size you select, the logistics, how close you can set up your facilities to get back and forth to the site, particularly when you're doing the offshore installation, and then this overall supply chain. And in the U.S., we're just developing a supply chain, so we have to be innovative in how we can jumpstart the supply chain, and particularly on small projects like the Hull project, where you're only looking at maybe less than 15 megawatts and a few foundations. It's going to be difficult to try to develop a brand new supply chain for that particular application, so you need to be innovative in what you're looking at as possible approaches. In site conditions, it's pretty simple, water depth probably being generally an important consideration in what foundation you would take. The water depths here are shallow. And then all the mid-ocean conditions from wind, wave, current, marine growth, scour, potential sand waves, which I hope you don't have. I haven't seen anything on that. Temperature conditions, and then icing conditions that may occur. Geotechnical, the basic profiles, the type and strength by depth below the seafloor. Common types are clay and sands, silts and gravel, mudstones, for example. And then in some cases you have boulders which present more of a problem, limestone, calcareous soils. None of those are really that present here. And then special conditions like earthquake. In some cases you have unique conditions like shipping channels and other things you have to work around. If you look at water depth as being a big driver, in shallow water, gravity base and monopiles have been proven. Suction piles have been demoed in wind projects with the actual turbines on them. Jackets haven't been used in shallow water primarily because of a cost. They're not likely feasible because of cost. We have an inward battery guide jacket which has been used in oil and gas applications in shallow water. In more of the mid-range, you'll see a move away from the gravity base and monopiles and more towards jackets and some of the other concepts in mid-range. And obviously as you go to deeper water depths, less than 60 meters, the jacket will be more prevalent. I didn't put water depths greater than 60 because we're really not looking at that at this point, but you go to floating structures at that water depth typically, and you need at least about 60 to 100 meters of water to go to a floating structure because of bottom effects with wave conditions. The Hull site, as it's been mentioned, is around 12 to 15 meters, or around 39 to 49 feet. It's considered shallow water. Gravity-based monopiles, a twisted jacket, or a suction pile are all possible solutions for this site. So we would encourage you to look at all the possible solutions. The site of an onshore manufacturing facility and availability of marine assets may have a big effect on the foundation you select. we'll talk about this later on in the presentation, but monopiles and gravity structures would be the obvious choice. If you go ask the Europeans, that's what they're going to tell you. It's been used there. But remember, they're working from a developed supply chain. They're working from logistics that are very easily to accommodate. They have all the marine assets. We're working from a different situation, so the answer may be different because we're limited. The willingness of the turbine manufacturer to provide loads for different types of foundations is going to be an issue. I don't know if the Siemens, Tom's still here, or GE, but it's somewhat of a challenge to get loads because they can only develop loads for so many different types of foundation types, and that's somewhat of a limiting factor. And as we go to more jacket foundations in Europe, and there's more evaluations of multi-pile structures, you'll see more willingness to use different types of foundations here in the U.S. The mid-ocean conditions, really, in this particular location, you have nothing in your mid-ocean conditions that would preclude the use of any of these particular concepts. There's nothing really there of any major consequence where you would say that you couldn't use any of the structures. So that doesn't really become a limiting factor. The tide range is not that great, 3 meters or around 12 feet, a little less than 12 feet from highest astronomical to the lowest. The storm surge is again around 3 meters, the maximum tide current about 1 meter per second, and the extreme wind speeds around 49 meters per second. That's pretty much a wind speed that's very common in Europe, Northern Europe, and that would be an extreme wind speed you would design for. Sea states of 6 meters of water is not great. The reason for that is in that water depth, the waves are breaking, so they can only achieve a certain height, so you don't get these large waves. You may have waves that are 12 meters or greater far offshore, but by the time they come into where the siting is for these turbines, they would already have broken, and that would limit the height that you can achieve at that site. I didn't see anything in the literature on sea ice or anything. Jim, did y'all have anything?
There's not much sea ice at this latitude.
Okay. As far as geotechnical, this is probably the most interesting thing, as Jim's already mentioned on the site. Clays and sands and silts, gravity structures sometimes in the weaker soils are limited. Monopiles and jacket structures, suction piles, typically have no limitations in most of those soil conditions if you can get the proper penetration. In your particular site, the reason why Jim mentioned that the monopile was going to be limited in that site is because the bedrock is relatively shallow. That means you can't drive the monopile deep enough to allow it to function in a soil that doesn't have high lateral resistance. And that's one of the reasons why you may not want to use a monopile in this particular location, is because you're limited by the depth you can install it without drilling into the bedrock. Other multi-pile structures may be a better option because their piles wouldn't necessarily have to be penetrating the bedrock. Again, the same thing applies to sand and gravity. Rocks present more problems. There are companies now that can go out and survey and tell you down maybe 30 or 40 meters down below the seafloor and identify if you have any small boulders or stones or that could affect the driving of piles. So there are some things there now that we have technology that's going to help us as we go forward to avoid insulation problems and reduce the risk. The geotechnical conditions, Jim's already gone over that. You have bedrock typically at 28 meters, and that's a controlling factor for monopiles that might be problematic. There's sands 3 meters above the seafloor, and then either an organic silt and a relatively soft clay. I don't typically, because I come from Louisiana and our soils are pretty mushy, the soil don't look that bad to me as far as the clay. It looks pretty firm clay from my experience. Also, you have a gravity and a clay silt with glacial tilt on one of the sites. The interesting thing is that those two boreholes are relatively close, and to have that much variation, almost totally different soil profiles, is very uncommon. And it'll require a real good siting study and know exactly what we're designing. And it could mean that the foundations could be quite different. One foundation could actually cost significantly more than another because the soil strengths are somewhat different, and that would have a pretty good impact. The weaker clay soils will limit the use of the gravity structure and the monopile. Turbine size is, I consider, as a trade-off as far as foundation cost and what have you. The bigger turbines with greater megawatts generate obviously more power, but they require greater blade diameter and hub height. That means the tower is going to require more steel, so you're going to spend more money for the tower to support that turbine. You're also going to require a stiffer foundation to maintain the natural frequency of the overall system. Again, that's more steel or concrete depending on what material you're using to build the foundation. Greater hub mass. As you go to higher megawatt capacities, the weight that you're supporting high in the air becomes greater. The blade weights, the rotary weights, and the cell weights all combined up to that mass. And so you require a stiffer tile to maintain that weight. Again, you're going to use more steel. The stiffer foundation is required to maintain the frequency there. Again, this is all driving the foundation to be heavier. So when we go to generate more power with larger turbines, we can assume that the foundation is going to be more costly to design that turbine. In the slower rotation of the blades, as the blade sweep gets larger and the blade length gets longer, it turns basically slower. And the system's frequencies then become approaching the natural or the frequencies of the wave loading that has the highest energy in it. So what this does is cause more hydrodynamic fatigue damage in association with the foundation, and particularly steel foundations, and that makes the foundation more costly to design for that. Turbine size, again, is trade-off, but there's some breaks here. The bigger turbine is going to require the manufacturing cost per megawatt to be less. It's going to mean the foundation installation cost per megawatt's less. If we design a foundation, we'll spend the money in building the foundation, but actually installing it offshore is actually going to save costs per megawatt because we'll be installing fewer foundations, and whether we're installing a foundation for a 5 megawatt or a 3 megawatt turbine, the installation cost is about the same. Fewer foundations also require fewer cables, and cable installation costs per megawatt goes down. And again, the OpEx and maintenance costs over the life of the structure is going to be less per megawatt because you'll have fewer turbines to visit, fewer to maintain. The hull turbine size, we were given a couple of scenarios to look at, and one scenario B was to look at some type of test stand where you would put a foundation test stand capable of supporting turbines from various outputs supplied by different manufacturers. And that'll impose some really unique challenges, and it may limit the foundation type. I'm not optimistic that that type of scenario can be really achieved, because trying to get a foundation to work for several different turbine manufacturers that all have different diameter towers and different frequency requirements for their turbines would be very challenging. The use of a foundation test stand designed for one turbine manufacturer, but may be capable of allowing that turbine manufacturer to develop his turbine. It's not uncommon for a turbine manufacturer to come up and release the first release of a particular model with one blade diameter, and then as they get more confidence in that turbine performing offshore, jump up in design. It's kind of what Siemens did with the 3.6, where they started out with a 107 meter blade sweep, and now they're up to a 120. So being able to test the full development of a turbine at a particular site may be an advantage. So if you had 2 or 3 sites here at Hull, and one site might be dedicated to one particular manufacturer, another site to another, they would use those sites to bring in maybe the next generation of turbine. The advantage to Hull is, over the long term, is that you would get the advantage at the end of having the most powerful turbine that generates the best power curves in the long term, and you would then allow the industry to test newer turbines that could be used further offshore. So there would be an advantage for the government to support such an effort in research in that, because you're helping the manufacturer produce a better turbine, there was some discussions about test stands for turbines. And so basically you could have, Hull could provide test stands for different manufacturers. The other scenario that was discussed is simply to have different types of foundations maybe with the same turbine, where you could test, because you have this unique situation where you have these different soils, it might be an ideal place to have 3 or 4 different types of foundations and then put one particular turbine on each of those foundations. Or maybe a combination of what I would call the second scenario B and C, where you have different types of foundations, but you also allow the foundations to receive different upgrades in a particular type or size of turbine. So there may be some advantages there in developing the project to take advantage of that. American logistics are going to be challenging. I mean, foundation designs, you have to consider that the existing fab yards with offshore experience, oil and gas experience, are along the Gulf Coast. When the wind industry developed in Europe, the wind sites were all in the same general area as offshore oil and gas in the North Sea. So the same infrastructure and the same expertise for fabricating were in those sites. And although up and down the East Coast you have a great history of shipbuilding and construction here, once a facility is closed for 10, 15 years, all the foremen and the superintendents that ran that facility, and a fabrication facility is just like the Army, is run by sergeant, a fabrication facility is run by foreman. Once you lose a generation there, it's hard to restart because you don't have that experience. And so even though you have the physical plant, you don't have the expertise, the hands-on blue-collar expertise to come up with this. So you have to generate some way of getting that done the best way you can. The best wind resources are obviously along this East Coast, but transportation costs are significant to bring it from fabrication sites around the Gulf Coast. New manufacturing plants are going to take time to develop. You're not going to get them. You know, you hopefully can get a plant done for this Cape Wind, but it's hard to develop a plant with only one project, and you need multiple projects to do it. The English have already experienced this. They have more wind resources than any other European country, but when they started developing and they issued the first round 1 and round 2, no turbines were built in the UK. There were no plants. Nobody was willing to put a plant in the UK to build turbines. Most of the fabrication was done outside of the UK. Now they're into round 3, where they're looking at 32 gigawatts of power, and all those sites have been awarded. So now there's a tremendous interest in getting close and building plants in the UK, building turbine plants, building sites along the coast to handle that. So until you generate an interest where there's a large backlog of volume, the investment's going to come slow in the infrastructure to build foundations. Went back too fast. The whole development should consider really at what's the most commercially attractive CapEx solution for this particular project. And that may be different than the long-term solution for the whole area. And sustained jobs are in the OPEX, which is the operational expense over the history. And OPEX costs in a wind farm are almost 50% of the total wind farm cost. So there's a lot of real sustained jobs in just getting wind farms out here. And getting the whole industry jump-started, I think, is the key. Another problem is with marine assets. The U.S. law requires installation vessels to have a keel laid in the U.S. to satisfy the Jones law. The Jones law is simply, if you come to the U.S. port and you make port, you have to leave and go to a foreign port before you can visit another U.S. port. So in installing a wind farm, once you install the first monopile or the first gravity structure, you now have established a U.S. port. You cannot use a foreign flag vessel to go to the next site and install the next foundation. You have to leave, go outside the country and come in. The oil and gas industry in the Gulf of Mexico gets around the Jones Act when they use big heavy lift vessels that are Dutch flagged or foreign flagged. They come in and they install one platform because they're only interested in one platform. And then they go to Mexico on the other side of the Gulf, get their ship stores, and then come back to install the next project. That's not possible when you're trying to install 100 foundations. And so that, or even 2 or 3 foundations in this matter, that makes it hard to use the best possible equipment. And so there's few vessels in the U.S. that are capable of installing foundations and turbines, for that matter, and towers. So it's something that really is a lacking in our whole supply chain that we need to address. And I don't have much confidence that the wind industry is going to be able to change this. There's a lot of reasons with shipbuilding and why the Jones Act has been around a while and has prevailed through a whole lot of lobbyists trying to change it. It's going to be difficult to do that. There's also some defense issues on why it should be the way it is. So in this particular case, the availability of U.S. vessels suitable for operations in the Atlantic, particularly in the swell conditions that you'll have, you can have relatively calm seas where you're only seeing maybe 1 meter or 2 difference in waves from crest to trough. But if they're long period waves generated by some storm far out in the Atlantic, they can have a great effect on a floating vessel. So you'd want to have some type of vessel that lifts up out of the water, hopefully, so you can work in those types of conditions. And that's going to present some problems because those vessels are relatively limited in this area. The most widely used solutions for foundations in shallow water are monopiles. They require large hydraulic hammers. This is another issue. The largest readily available hydraulic hammer in the U.S. is an IHC S200, a relatively small hammer. To drive a large monopile, you need an S1200. To get one of those to mob and demob across the Atlantic, you're talking about millions of dollars that you add to the installation cost for maybe 1 or 2 foundations you're trying to install. That's a significant problem. And then you add to that the exchange rate that's been going against us for a long time here. Back just a few months ago, early in the year, 3 months ago, the exchange rate to a euro to a dollar was a 1.32. Now it's 1.46. If you add that cost and you get caught in this cost and you have a whole bunch of your equipment coming from Europe and the exchange rate continues to go in the wrong direction, that's a great risk to your installation budget. There's also a lot of special equipment that's required for installing. There's lifting tools, special handling tools, guides that keep caissons and monopiles vertical. A lot of this stuff is available in Europe, but not available here. Even the bottom site preparations for a gravity structure, in order to put a gravity structure out in some of these areas, you would have to remove maybe 1 meter or 2 soil in a large area around the site and the pad where you want it to come down with the gravity structure. That requires some special equipment. Those dredge devices are not readily available. I guess I'm going a little long. So foundations are going to require special considerations, possibly solutions without driving or driving with small hammers. And I guess I'm just going to run over some of this stuff. I think this is interesting. The worldwide offshore supply chain was started in this country. It was then exported to Europe and that. And there's links to that chain that are available that you should consider in jump-starting the offshore wind industry here. In the early days, the oil and gas industry borrowed a lot of the technology from aerospace, from the space program. And I think the wind industry here in the States can borrow a lot from the oil and gas industry and develop quicker by using that as a jump-start capability. For small developments, particularly like Hull, I think that's something you have to look at. And I think it's important to have American engineers involved in the project, because when you bring Europeans in, they don't realize what the limitations are. And they may come up with a solution, but it may not be the most economic solution. So I think it's important not necessarily to have a 100% American control over design, but I think it's important to have American influence in the design. Again, the foundations are going to be limited by the supply chain, and small developments are hurting there. This slide often strikes people as interesting. There's 10,000 parts to a monopile. 10,000 pieces of steel, bolts, nuts, angles, grating to assemble that. In Europe, those monopile assemblies come in from all different countries. The monopile itself might be rolled in Germany, where the plate is coming from a German mill. The actual TP, or transition piece, may be built by a Danish company. The components from on the TP may be built by a Polish company. And all that is generated in how to get the best cost factors to generate the lowest cost. And so there'll be opportunities for components in the wind industry to come from all over this country. These are some costs. The breakdown on the right just shows the basic cost. Substructures are around 16%. There's an installation cost. Part of that is with the actual installation of the foundation. The other part is with the installation of the cable. But if you look at some recent monopile cost over here, these are some recent projects. They're running right at around $1 million for the foundation. That was based back when we were using 1.34 as the factor. But if you take the cost in euro and what it cost to develop these three recent projects, they would run somewhere around $800 to $1 million per megawatt. So I think when you look at your project here, you're going to have to be looking at those types of numbers. This cost of foundation is typically about 30% of the total cost. This is projects that are available and have been built in the States, large jacket structures. This is what a European jacket yard looks like. That's just a few months ago, that's a jacket under construction for a wind tower in offshore in the North Sea. This is a lift boat installed in the tower section. This is actually a vessel that was built in the Gulf of Mexico. It's a Dixie-class lift boat. Siemens was using this to install a foundation in Europe. So there are U.S. flag vessels that can install towers and nacelles and blades. This is a new capability of structure there. Installation vessel, that's a new vessels. These are our concepts here. And I'll take your questions. And I probably want to look too long.
Thank you so much, Rudy. Coming all the way up from Nolans.
Nolans.
All you get is this hat.
That's
Josh,
okay.
thank you so much. And we're going to continue with the finance panel with Jim Duffy and Tony Grapponi. Great, great. Where's the clicker? Someone take my clicker? I think we got it right. Awesome. Great. Well, very good. Now we're getting into one of the more important aspects of any project, clean or dirty, is the financing. And in order for projects to be built, they have to be financially viable. And on the panel today, we have two experts in the field. We have Tony Grapponi to my right. He is a partner at Novogradac & Company in their Boston office and does a lot of financial analysis and structure for clean energy projects, specializes in wind and solar, biomass as well, Tony?
You name it.
You name it. And next to him is Jim Duffy, partner at Nixon Peabody, and he runs their renewable energy practice out of the Boston office. Both Tony and Jim's organizations also run very similar conferences. I know Tony just had a very successful conference out in San Francisco.
That's correct.
And I've been very fortunate to know these two gentlemen. They're really great for the industry and great leaders. We'd like to start off with with Jim. So please welcome Jim Duffy.
How do I do this?
Okay, there you go, left and right.
All right. Thanks, Andy. We sort of told Andy he had to moderate or we wouldn't do this, so he's part of the panel too, even though I noticed he didn't take a seat over there yet. Tony and I did what we're about to do now in 45 minutes over a full 2 days, 2 weeks ago. So if we sound like we're going a little fast, it's because there are a lot of details here that we're going to skip over a little bit. Plus, nobody's done one of these before, so the financing is rather speculative as to how Hull would actually finance a project. So I'm going to go through some of the federal tax incentives and then some of the transaction structures that are typically used when private parties are either developing on their own or in partnership with nonprofit or public entities. So, and I should say, I have a brother who's in the renewable energy industry that some of you may know, my brother Dennis, and he told me once, I never knew when I got into renewable energy that I'd have to know the Internal Revenue Code like I do. And that's the way the federal government chooses to subsidize a lot of this. So bear with us if we quote the Internal Revenue Code more than you'd like us to. So a couple of overviews on this, a couple of slides. One is, I tend to think there are 4 stages of finance on a wind project. The first stage is what's the initial stage, and that's where you write checks. Nobody lends you money. Very few people give you grants because you're figuring out if you even have a project or not. Fortunately for Hull, they're pretty much through this stage or through a lot of this stage. But that's if you're a private developer where we tell you, unless you got $1 million, don't start down this road. If you're Cape Wind, unless you have $40 million, don't start this road. But you know, this is where you spend your own money. Then you get to the point of actually ordering the turbines, deciding which ones you're going to get. That can be very difficult to finance. Sometimes, in fact, before the economic markets collapsed in 2008, you used to be able to get loans to make your turbine deposit with. It's a big check. But the problem is it's very difficult for a lender to get comfortable with that kind of loan these days because you don't have all your permits yet. You don't really know where the project's going, so if you don't go forward, the collateral the lender has is a turbine, and then they have to find a place to use it somewhere else. So it's a very risky loan from a lender's perspective. So that's expensive money. So hopefully when you actually get your permits and you're ready to install, you get your construction financing, and that's more reasonably priced because people see a real project on the horizon. And then finally, the operating stage, and that's where I'm going to talk about here today, where you repay your construction loan with some combination of money being paid by someone who can utilize the tax benefits that we call the tax credit equity investor, or maybe by just getting a Treasury grant, but that's probably not going to apply in this situation because it's probably going to expire. Any state or local grants you can get for actually operating the facility. Developer equity, which is the part that no developer really wants to use and they hope to minimize, or project debt, which could be secured by whatever operating revenues come out of the project. So I'm going to then talk mostly about the tax incentives that bring you the tax equity investor that helps pay down the cost of the project. The universe really changed in tax equity investing in 2009 because when the economic markets collapsed in 2008, all of a sudden the big companies didn't need tax credits anymore. And the reason is they had no profits, they weren't paying taxes anymore, so a tax credit wasn't really very useful to them because they had nothing to credit it against. So the rules changed, and I'm going to get into that. But until then, the principal incentive for wind, and it's still a major incentive, is what's called the production tax credit, or the PTC. But with the stimulus bill, ARA last year, or the year before last now, developers have an option of taking production tax credit, investment tax credit, and I'll get into all these, or a federal grant in lieu of tax credit. I like to think of it as kind of going on, let's make a deal with Monty Hall, and you've got 3 doors, and you got to figure out which one works for you. And Tony will run 3 models for you, and you make a wild guess. So I'm going to talk about those 3 credits. Production tax credit. And it's in the Internal Revenue Code. It's available for all these types, wind primarily, but I know the Hull Institute's talking about some other types of energy. No longer used for solar after the Energy Act of 2005, but many other types of energy. What's a tax credit? I think I should say that for any beginners here. A tax credit is you, as a corporation, and these are generally for corporations, you get your income minus your deductions, and then you figure out your tax rate on the difference, and you say, aha, I owe so much in federal income taxes. Then you subtract from that number the amount of the tax credit. So it's a full dollar-for-dollar reduction in what you owe the Treasury. So the key is you have to owe the Treasury something to make it worthwhile. Compare that with a deduction, which really just reduces your income. So if you're in a 35% tax bracket, like most corporations are, a deduction is worth 35 cents because you would have paid 35 cents of tax on income that now you don't have to list on your taxes. So a deduction's worth 35 cents, a tax credit's worth $1. Key distinction there. The Treasury also plays some games here with deficit reduction, how they're going to reduce the deficit going forward. Right now, a wind facility has to be placed in service before January 1, 2013 in order to be eligible for these production tax credits. The other types I listed there have until January 1, 2014. Now, everyone in the industry assumes these will be extended another year, another 2 years at a time. The problem is, if you're not going to be placed in service by 2013, no one will invest in your project today for tax equity because there's the Internal Revenue Code right now says there are no tax credits after that day. So the Congress extends these a year at a time so they can always say we're reducing the deficit over time because they pretend the production tax credit will disappear in 2013, but everyone knows it really won't. So, you know, that's the gamesmanship of Congress. It's why the U.S. is behind in renewables in many ways. What is the production tax credit? It's a credit based on the production. So for wind, for this year, it's 2.2 cents per kilowatt hour of electricity, and this is the key, produced by the taxpayer and sold to an unrelated person, and you get this credit for the first 10 years of operations. So the amount of the production tax credit is an operating subsidy in theory over 10 years. Now, the problem is you need, and certain types of energy only get half as much PTC. Some say it's because they don't need as much subsidy. I tend to think it's because their lobbyists aren't as good as the wind lobbyists, but you know, you can figure out on your own. Produced by the taxpayer means the owner of the facility gets the tax credits, subject to some bizarre exceptions for biomass. So you can't just earn a tax credit and sell it to an investor. You have to make the investor who gets the credits has to be an owner of the operating wind facility. Why do you bring in a tax equity investor? Well, either because the owner of the facility is not going to have enough income tax liability itself, but more importantly, the investor pays you up front for a 10-year stream of credits, and you use that money up front to finance the project. So you run all these financial models, figure out internal rate of returns, expected production, and you come up with how much the investor pays to be assigned the rights. Typically, a developer brings in a tax equity investor who really doesn't want to know anything about the wind turbine, just wants a financial, they're treating it as a financial instrument. It's probably through the treasurer's office of some corporation or bank who's trying to reduce the tax liability. So you tend to form a partnership. And here's a really simple structure. Oops, pushed too hard. Your investor, in namesake, gets a 99% interest in the entity that owns the facility. The developer, who does all the work, gets a 1% interest. Now, you might think that's unfair, but you know, there are accounting games that Tony can show us as to how the money might not go the same way that the tax credits do. Tax credits are reduced by up to a half to the extent you have below market financing or grants financing the production. The problem with this is they are saying, well, you're already getting cheap debt, therefore you don't need tax credits. Well, we know we need both. We all know that. But this has to be taken into account when you structure one of these deals. So below market financing isn't necessarily a good thing because it costs you tax credits. If an investor decides it doesn't have tax liability, it can sell its investor for the balance of the 10 years. And the Treasury recalculates this 2.2 cents per kilowatt hour subsidy every one of the 10 years that you're eligible for it. So you don't, it's all based on a black box formula that you can't figure out. It's top secret at Internal Revenue Service somewhere. But as you can see, it's gradually creeped up since it was 1.5 cents back in 1993 when the program was first adopted. I'm going to skip real quickly over this revenue procedure, but it's in the materials, and there are copies of the materials at our table in the back corner, and you'll get them online later. There are rules to make sure that your investor isn't really a disguised lender who calls himself an equity owner. Things like the developer can't have less than a 1% interest. They can't have their interest magically change to less than, the investor's interest can't magically flip down to less than 5%. Things about puts and calls between investors and developers that are beyond the scope of a 40-minute presentation here. Things about the investor's money being really at risk. This is all to make sure they're really an investor. So what else does the investor get besides the tax credits? They also get depreciation deductions. Those are the things worth 35% because they write off the cost of the facility. In this case, over 5 years. Now, you know, a hotel like this would be what, 40 years, 39 years? 39 years, something like that. Wind, well, we all know it lasts for more than 5 years. You get to depreciate it over 5 years. And in a bonus for this industry, which had nothing to do with adopting it, the bonus depreciation means you can basically, if you were to place in service this year, deduct 100% of the cost of your facility in the first year, or next year, 50% of the cost of the facility. This is another one of the bonus depreciation is another thing that the Congress extends periodically in short-term increments because they feel the economy needs it.
Right, it's not necessarily bonus depreciation in the sense that it's extra depreciation, it's really just accelerated depreciation. So instead of taking it over, like you mentioned, 39 years in the case of a hotel, with a wind turbine, you write off the entire cost in the year that you start operating the facility. So it's not bonus as much as it's just very much accelerated.
Yeah,
right?
they call it bonus, but
exactly.
it's just faster. And this is another benefit that the investor gets when they, in namesake, have a 99% interest. They also get some of the cash, although you try to steer as much as the cash as you can to the developer, but to the extent the investor is underwriting it, it's one of the components. Payments for electricity, monetization of RECs, or any state operating subsidies. And you know, the cash flow varies dramatically in these deals. A lot of offshore, probably it's close to zero because you know, these aren't cash cows like some of the onshore ones are. And then the investor wants to get out, so they probably get out once they've got the tax benefits. They're not in it for the long term, these tax equity investors. So their return, and they plug it into an internal rate of return, is how many production tax credits am I going to get? How many depreciation losses? When, at what years am I going to get them? How much cash, if any? Compute internal rate of return and decide, I'll give you X dollars for 99% interest in that project. And you probably will have no idea where these numbers come from. They'll vary all over the place, but somebody like Tony will be running numbers and figuring them out.
So yeah, so just to kind of step back a little bit here, to kind of reinforce a couple of points. So it's very common when you have these federal tax incentives involved that the facility, the wind facility, is owned by a partnership, and the partnership has to have more than one partner. So usually there's a general partner that sponsors it, and then that general partner sponsor generally doesn't bring a lot of capital or money to the project. Instead, what they bring is a lot of effort and know-how, and then they oftentimes don't have a need or can't really use all these very generous tax incentives. So in order for them to monetize these generous tax benefits that the project qualifies for, they admit, often like a silent limited investor partner, like a big insurance company or a big bank that has plenty of tax appetite to use these very attractive tax incentives. So the general partner sponsor, again, they create a partnership. They admit an investor who can take care of the benefits, and the general agreement is the general partner sponsor is going to really operate or manage or develop, basically develop, construct, and operate the facility. And then the limited partner is going to come in as a silent partner, but the limited partner is going to get allocated, say, 99% of the primary tax benefits and losses and potentially some cash. And then in order for the general partner sponsor to get incentivized to do it, the general partner will probably charge the entity some sort of fees in order for them to get some cash to make it worthwhile for them to do the project.
Yeah, and you'll see that when Tony does a hypothetical financial model in a few minutes. So there was sort of a sea change in this in 2009 with the stimulus bill, where wind developers now have an option, as I mentioned earlier, to take this production tax credit of 2.2 cents per kilowatt hour or an investment tax credit. Investment tax credit has been used for solar since 2005, and it's been used for other, historic rehab and other types of tax credits through Internal Revenue Code. So it wasn't new, but it's out there. It's a whole different structure. It's 30% of the qualifying eligible cost of the facility. So it has nothing to do with how much electricity you produce. It only is based on how much it costs to build the facility. So it's like apples and oranges, and you run your two models and decide which works best for you. I would say these days most people are opting for the ITC. Last year we only closed one deal that claimed the PTC, and that was with a 42% capacity factor. So you could tell they had a lot of wind, a lot of production based on the cost. But that's higher than any numbers we're talking here, at least on Jim's 30 to 35% estimate. So this may well work out better as an ITC project. Certain costs don't go into the basis of the facility. Simple examples are operating reserves, permanent loan fees, things that are not related to the development of the facility. The cost of transmission generally does not go in. So that is an important component that would not get a 30% credit here. But where you draw the line between the facility and the transmission and how you allocate the dollars between the two is let's just say it's an art. You get the full investment tax credit the day you start operating. You don't get it over 10 years, you get it all at once. You can't just go in, get the credit, and sell off the property. It only vests 20% a year, so you have to stay in the deal for 5 years, or you recapture the unvested part of the investment tax credit. The ITC, you don't have to sell to an unrelated party. You can own it, use the power yourself. And when you claim the ITC, it's good for distributed generation. Probably not what we're really talking about here offshore, but it's different. The ITC also reduces your available depreciation by half of the ITC you claimed. Since you're claiming a 30% ITC, half of that is 15%, meaning you only get to depreciate 85% of the otherwise depreciable basis of the project. Under PTC, you depreciated the full basis. Why? I don't know. That's what Congress decided. Who knows? You can use leasing structures with ITCs to pass through the credit to a lessee. You can't use that on a PTC because that's the way the code reads. ITC can use below market financing or grants to finance the project and not reduce the amount of the tax credit. You can't do that with a PTC. There's something called the alternative minimum tax, which says no matter how many deductions and credits you get, you got to pay at least so much tax, because there are these corporations that paid zero income tax, became somewhat controversial. However, the ITC can reduce that alternative minimum tax to zero. The production tax credit can only reduce alternative minimum tax for 4 years of the 10-year period. That also makes no sense, but it was part of the lobbying process to get the credit adopted. And finally, your third option is a check from the Treasury. That might seem the most attractive, but it was a short-term thing because there were so few investors with tax credit appetites in 2008 and 2009. Right now, it only applies if you commence construction this year. In fact, it originally was going to expire if you hadn't commenced construction last year, but at the last minute in December, they extended it for another year. Will that happen again? Well, we've spoken with chief tax guy for the Senate Energy Committee chair, and he says there's no way it's getting extended. Now, he also said the same thing a year ago, but yeah, I certainly wouldn't count on it.
I believe it's in Obama's budget.
Yeah.
But who knows if it'll actually ultimately pass.
Although it's funny, in the December negotiation in Congress, the Obama administration said we don't need to extend it even to this year. And then, as part of getting it through the Congress, he had to back off on that. So that's a dollar for dollar Treasury grant in lieu of claiming the investment tax credit. Treasury is supposed to fund these grants within 60 days. I don't know. Sometimes they do, sometimes they don't. If they decide to ask questions, they can extend the period. So if they're not ready, if they're overwhelmed, they'll find a question to ask.
Yeah, the ITC and the cash grant program, they're supposed to be for the same dollar amount, but the process works very differently. With the investment tax credit, the taxpayer claims the amount of the tax credit on their return, files their tax return with the IRS, and chances are they'll never hear from the IRS again. With the cash grant, it's very different. You have to actually apply to Treasury and request request Treasury to write back to you and give you a check for the amount of the grant. So that's very different. When you do the grant, you're essentially saying to them, please audit me, you need to audit me, you need to approve this. Whereas the tax credit is very different. You just claim it, and as long as you basically follow the rules, you'll be okay.
Yeah, and what Treasury generally does is send your package to NREL and ask them to analyze it and tell them if that's a reasonable cost. And you'll get an answer from Treasury, but you don't get to talk to the NREL guy who told Treasury what to tell you. So it's very difficult to negotiate if you get an answer you don't like. Like all of a sudden you thought it was a $10 million grant, ends up being $8. You never really get a clear explanation why. So for that reason, it's not perfect. The other thing is these grants only monetize the ITC. They don't give you a monetary benefit for the depreciation. So unless you can use the depreciation yourself, you probably still need a tax equity investor to take advantage of the depreciation.
And just to remind folks, it's only the investment tax credit that you can exchange for the cash grant. You can't exchange your production tax credit for the cash grant.
So you have to opt out of the PTC into the ITC and then decline that and take the grant instead. The cash grant program also can't be made to governmental entities or nonprofit entities or instrumentalities thereof. Now, there are ways to get around this. We think it was actually a mistake when they put this in the code, but then they realized it would cost more money if they corrected the code. So what we've done on some deals is have a nonprofit form a for-profit, wholly owned for-profit subsidiary that claims a tax grant. And then you have to pay tax on the actual wind project itself. Or in a governmental entity, because they use the term instrumentality, and instrumentality has a whole legal meaning in the Internal Revenue Code that the Congress didn't realize when they passed the bill. So you actually have to have the governmental entity, and this may come to play here, set up like a friendly nonprofit, which in turn has a taxable subsidiary. And we did the Santa Barbara, California deal that way, but it unnecessarily complicates deals. On the ITC, the only thing you don't get is the 1% ownership that the municipality maintains. The 99% still goes through to the investor.
So if you're doing an investment tax credit transaction and you have a general partner or any partner in the partnership that's a nonprofit entity, it's eligible for the ITC. However, you essentially waste the investment tax credit to the extent it gets allocated to a nonprofit. But the entity in itself is eligible for the ITC. Very different with the grant. With the grant, if you have a tax-exempt entity or a nonprofit in there, technically the partnership isn't eligible for the grant. There are some potential solutions in some cases to that, but you just want to be very careful if you have a tax-exempt entity or municipality that somehow has some direct or indirect ownership interest in a partnership that's trying to get a grant. So
your government is here to help you, and they make up all kinds of rules that make it, I don't know. This is the way it works out in the legislative process. There are three more or less standard financial models used to finance these deals where there's private developers. The so-called flip model, which is often used on production tax credit deals, the sale leaseback, which can only be ITC or grant deals, or the lease pass-through, sometimes called inverted lease, which is only ITC or grant. I'm just going to mention these really quickly, but again, every project has its own benefits. In the flip deal, which is the simple one, the developer has 1% and all of a sudden their interest flips up to 95% once the investors got what they want out of the deal. The investor starts at 99, flips down to 5% once they've got all the tax benefits out of the deal. The partnership sells the power. If the developer wants to get the investor out of the deal, the investor only holds a 5% interest once they get the tax benefits. So it's easy to buy them out because you're only buying a 5% interest. That's the model that developers use if they want to get rid of the investor really quickly and not have to deal with them. The sale leaseback, the developer builds it, sells it lock, stock, and barrel to an investor who gets all the benefits. They get all the tax credits, all the depreciation, because they own it. They lease it back to the developer to operate, and the developer then sells the power. You don't do this if you want, as a developer, if you want to own the project down the road, because now the investor owns 100%, so you have to pay them 100% of the value of the property to get rid of them, as opposed to only 5% under the other model, and the releasing rules that have to be complied with. The sort of middle ground between the two is with the lease pass-through. The owner, where the developer owns a significant interest, leases the project to an entity where there's an investor. That entity that leases the project sells the power, and that entity that, in the middle here, this entity in turn owns an interest in this entity and gets some of the depreciation, generally less than half, probably enough to shelter the income from their investment. This has complicated rules of its own, but the nugget or takeaway here is these are the three basic structures that people tend to use. And now Tony's going to give you a very hypothetical example of how it might work.
Great, thanks a lot, Jim. I appreciate that. So, as Andy mentioned earlier, my name is Tony Grapponi. I'm with Novogradac & Company, based here in Boston. Just quickly about our firm, Novogradac & Company is a traditional kind of accounting firm in the sense that we provide, all of your typical audit and tax services. However, the firm is different than your traditional CPA firms in the sense that we focus our services on projects that generate some type of federal or state tax credit. And renewable energy projects, because they throw off these types of tax credits, is a natural place for us to kind of focus our energy and efforts. We've got a bunch of offices across the country. We're headquartered in San Francisco, and basically we have offices in pretty much all of your major markets. We do have a booth down there in the back of the room too, where we have some, our firm publishes a journal of tax credits. There are some great articles on some renewable energy projects that have been done across the country. I encourage anyone who's interested to go back there and grab a journal for themselves. I'd like to thank Andy as well and the Town Hall for inviting me to speak today. It's a real pleasure to be here, and I look forward to kind of going through some very, very hypothetical numbers on a proposed project that might bear some similarities to what could happen here in Hull. Okay, so just to kind of revisit the organization structure that Jim just went through, again, oftentimes you have a partnership. When you're trying to take advantage of these federal tax incentives, you create a partnership typically. This would be the Hull Offshore Wind Project Partnership. There would be some sort of project sponsor. In this case, we're assuming that it's some for-profit entity because they may in fact go for the grant, and as a result, we're going to have a for-profit general partner. We're going to have a developer. Now, this developer, they may be, sometimes it's not uncommon for a developer to be related or affiliated with the general partner, but it's not a requirement. Sometimes they're just affiliated, and the key is that you get a qualified developer. Again, hypothetical. Okay, so you're also going to go out there and you're going to try and find a tax equity investor. Again, they're going to get 99% of, say, the losses, the tax credits, depreciation, that kind of stuff. And then you're also going to need a senior lender to provide a permanent loan to the project. And then you'll probably even need some other source of money to come into the deal. And you can see the solid lines here going down to the project entity. They denote ownership lines, and then the dashed lines represent these are other entities that are going to provide some financing sources to the project entity, but not in the form of ownership, probably in the form of a loan or debt or something. Great. Hypothetical scenario. What we're looking at here today is we're looking at actually it's 4 machines. Each one's a 2.5 megawatt machine. And we're assuming that it's going to generate a lot of power, say 30.5 million kilowatt hours a year, which I think in this scenario equates to somewhere around a 35% capacity factor, kind of rounded off a bit. Factors to consider when you're trying to do an offshore wind project. Folks have talked about these issues throughout the day. We'll just kind of remind folks, you've got economic factors, very important. How do you pay for the project? That's what we're going to focus on today. Obviously, there are development issues, which you've already covered, as well as the permitting issues and so forth. And then ownership issues, which is some of the topics that Jim went through just a moment ago. Project costs. What types of project costs are we going to incur? Obviously you're going to have your machines, your component costs, some professional fees, hopefully. You're going to have construction, actually installing the site. There'll be insurance, some soft costs, those types of things. Obviously permitting is another cost that gets added onto the project. Taxes, potentially some other fees. Financing costs. Obtaining construction financing or obtaining permanent financing, these are all other costs that go into the process. There's obviously transmission.